Software Engineering Radio, episode 29, Concurrency, part 3. Hello everybody, welcome to this episode of Software Engineering Radio. This is Concurrency Part 3. However, before we start talking about concurrency, I want to comment on some of the comments we got from you, the listeners, specifically on those that complained or hinted at some of our sound problems. So we got several messages that said, content's great and all of that, but your sound is not too good at times. There is echo, voices are not loud enough. If there are two people on the podcast, one voice is loud, the other voice is rather quiet. We know about these problems, we're aware of these problems, and we're working on that. The problem in our case is that we're a team of people who record those things. So we don't just have one recording site where we can optimize things. We have various people who record things. We have various software packages, various operating systems. So everybody has their own personal challenge in recording a good sounding podcast episode. We are aware of the problem, and we are working on that. I've also been purchasing additional recording equipment with preamps and all that. However, keep in mind that it will probably still not sound like a really professional recording. This is really hard to do in this kind of distributed setting where we record our episodes. And so we've already recorded a couple of episodes. So those will have the usual, not so great sound quality, but the forthcoming episodes, probably from episode 34 or something onwards, will have better sound quality. Okay, so that's all for that one. Let's go on with the topic for this episode, which is concurrency, part 3.
Welcome to our third episode on concurrency. While we focused in the first two episodes on the very basics of concurrency, this time we will talk about how to build highly scalable servers. Especially we will talk a lot about the reactor pattern and how it is used, and how servers can be built to be highly scalable. So if you take a look at application servers, you can divide them into two different kind of application servers. Michael, I guess you have an opinion which kind of application server is better suited, or how we can divide the application server area.
For this discussion here, I would differentiate between event-driven servers and data-driven servers. For an event-driven server, I would see a large number of concurrent requests from users or other systems, and for data-driven applications, this is typically the domain of batch processing, data analysis, heavily algorithmic centric. And so I know that there is no black or white. A server is not only event-driven, but for this discussion and to better distinguish the systems, I would make this distinction. And in the later discussion, we focus mainly on the event-driven servers, because for the data-driven servers, different patterns are applicable to optimize them.
Yeah, so could we say most of the servers we have in our daily business, web servers, EJB application servers, they are all event-driven application servers. Is that correct?
Yeah, to a large extent, I would say they are event-driven. The way we use them as web servers, as general IT infrastructure servers are typically event-driven, I would say.
Okay. Before we discuss how to build them, what are the major problems? What are the factors that lead to low performance or scalability on these event-driven application servers?
Yeah, some of the key problems that I see, and I learned this from Doug Schmidt when we did middleware optimizations, is that dynamic memory allocations, for example, or generally dynamic resource acquisitions lead to a high percentage of overhead in the algorithms, in communicating, in dispatching events. Further, there's a synchronization overhead on shared resources when you have concurrency. And thirdly, it's the waiting time on blocking synchronous calls. So all three areas are important to address. The fourth one is like a resource shortage when there's really no resource available anymore, but I don't consider that so important because then we have a failure anyway. And to deal with resource shortage when there are no resources available anymore, this is a really hard topic, and I know almost no application or no server that can properly deal with it.
Okay. I'm not sure if we already defined the terms in previous episodes, but I guess we should divide or define the words scalability, performance, and throughput. I mean, these are the most important characteristics of application servers, and they mean different things. Could you just give us a few words on this?
Yeah, I would first refer to Architecture 2 episode where we have discussed this briefly, but for here, scalability, well, what is scalability to us? When doing upscaling, so when increasing the load on the system, ideally we want to have the same throughput, we want to have the same quality properties for the individual requests as we had for the lower number of requests. But realistically, it is not like that. So in the best case, we have a linear degradation. And in the worst case, which is then where we are not satisfied, is when the system would perform really poorly at a certain limit. For example, with 10 users, the system works fine. With 100, we realize some degradation, and with 1,000 users, the system would just not react anymore in any timely manner. That would be poor scalability. But if the system would just be somewhat slower with 1,000 users, then we would be satisfied. We would have scalability on the system.
Mm-hmm. But there's also the scalability, this scale out versus scale up thing. How if you add hardware, how you do it? If you add a additional server to a cluster system, or add a much faster CPU or whatever the bottleneck is.
Yeah, so scalability is also whether you can actually change your configuration to deal with higher system loads. I mean, you're not scalable when your system cannot be extended, and so you run into this problem of poor throughput and poor performance really early when your system cannot be extended. So extendability is kind of a property necessary for scalability. Was this what you were hinting at?
Yeah, exactly. I mean, this scaling up or scaling out thing is exactly that, how you modify your hardware or your system to add more performance to your system. I mean, you have two ways, basically. You can buy a faster CPU or hard drive or whatever the bottleneck is. And the other way is to add, a new server to the server system, to a cluster system with more than one server, add a new CPU or whatever, an additional hard drive, and it still has to scale out in this case.
And how we measure scalability, here not only performance is important, but also the throughput, which is slightly different than performance, or is contained in the performance figures, and also latency and the jitter of requests. All those properties qualify a high quality system from a poor quality, from a poorly behaving system.
Mm-hmm. Can you just drop a few words on on throughput, latency, and jitter? What does this mean actually?
Yeah, you could measure when you talk about the measure units, you can explain throughput, latency, and jitter. So in case of throughput, this is how many requests per second get through your system, and throughput doesn't tell you anything about latency. Latency is what was the delay incurred, the delay imposed on the system when the request arrived until it was served.
Okay.
Taking those measurement points. You can also think of other measurement points. And jitter is like the difference in the delay that is introduced by the system. When there is large jitter, then it, for example, one request might take in one case 1 millisecond, and in other cases it takes a complete second until it gets served. It's so important for systems that are interacting with users, because then the users don't know what to expect from the system. When it's generally slow, when every request, when every mouse click takes 2 seconds, it's okay for the user. But when it's really fast and when there's a good user experience and suddenly it drops, then the user doesn't know what to think of the application and is confused and might click twice, 3 times because he thinks he missed the button or things like that. So here it's also important to stay within some bounds of jitter.
Okay, I see. And I guess if you try to optimize one, and not all the other characteristics are optimized too as well, or maybe they're even contradictory sometimes.
Yeah, it's like balancing forces. It's like balancing these 3 properties together with other quality attributes like maintainability and flexibility. So you have to find trade-offs and find a good configurations that fulfill your requirements.
Okay, what can we do to optimize all this?
Yeah, I would start off with the reactive design, mainly described by the reactor pattern. So when we have an event-driven application, a reactive or event-driven design is the best way to deal with those requests, with those events. The reactor pattern allows to wait for multiple events from multiple sources using a single or multiple threads. And the key property of the reactor is that it separates the waiting and dispatching of events from the handling of events. So you have event handlers that you register with the reactor and say, well, I want to wait for this kind of event on this event source, and then the reactor puts that into its list of event sources that it waits on. And the typical call in current OSs is the select call that is used to wait on those events. Reactor can be used in a single or in a multi-threaded environment. In a single-threaded environment, of course, it's more easy and the design is more clear, and a single threaded reactor implementation is very well suited when you want to avoid all the difficulties associated with concurrency. And so the single threaded reactor implementation avoids synchronization overhead. It and minimizes the dynamic memory allocations, because you just have no concurrency, and that is often a good alternative. So a single-threaded reactor design is a good alternative to concurrent applications. But on the downside, you might have not the high CPU utilization that you require, or so you don't use your resources optimally in some circumstances. And having multiple CPUs and having this application, the server application, being the sole application running on a CPU, on a multi-CPU machine, you don't gain the benefits of having multiple CPUs. So there are reasons and situations when you want to have a multi-threaded reactor.
Of course, and you said it, the cure is the multi-threaded version of reactor. I guess there are different ways how to use it multi-threaded.
in simple multi-threaded application servers, there are models implemented like thread per connection or thread per request. In thread per connection, you would have for every client connection, you would have a dedicated thread that could even block on a read call and then just serve this request. But of course, if you have multiple connections, if you have really many connections, you have a resource bottleneck. So you're tempted then, and you should use the reactor. Same is with thread per request. Spawning a thread every time a new request arrives also doesn't scale really well. What you want to have, and what is much better, is a flexible association between connections, requests, and threads. And here thread pools come into play. But first, going back to what's really difficult in a multi-threaded reactor environment, this is the synchronization overhead, firstly. And secondly, the concurrency often demands memory allocations, dynamic memory allocations, for example, for the queues, because anything that you exchange between two threads must be allocated on the heap and not on the stack. Of course, you could pre-allocate, eagerly acquire, to talk in the terms of Pt.3, you could eagerly acquire the memory and then share it between the two threads. But often, for simplification reasons, this is not done, and therefore a source of overhead. And the third part is that a third issue challenge is that you consume quite many resources, as in the case of thread per request or thread per connection. The number of open connections and the number of threads can be quite high.
What kind of measures do you do to cope with this?
Firstly, I mean, now I'm going to iterate through a list of patterns and concepts. For example, thread-specific storage can be used when you have data that is thread-specific or thread-local. Basically, avoid to have shared resources. Another key pattern is like reader-writers locks to minimize synchronization overhead when there are more readers of a variable, of a synchronized or protected variable, than writers. And in other words, the read access occurs more frequently than the write accesses.
Can you I am not sure if we already did it in the second episode of Concurrency. We didn't define reader-writer locks, I guess, did we?
No, I don't think we discussed them yet. So having this key assumption that the read accesses are much more seldom,
the write access.
Having this assumption that the write accesses are much more seldom than the read accesses, you know that a read access doesn't really harm when it occurs concurrently. So you can allow many concurrent reads on your data, but as soon as there is a write, you should make sure that there is no more read on the data.
So the read doesn't block at all, just the write.
Yeah, the read doesn't block unless there is a write concurrently acting.
Okay.
And then the readers will be just queued and until the write is finished, and then they can start reading again. And similar it is for the writer. The writer is blocked as long as there are still readers reading it, and now of course you can juggle a bit with priorities of who's more important, the writer or the reader, who has to wait for the other. But there are some typical resolutions to this that a writer, because it's more seldom and it's more important that you have current or actual data, that you give the writer a higher priority than the readers.
Okay, I guess condition variable is pretty close there.
Yeah, a condition variable allows you to suspend a thread while waiting for a certain condition to be true. And so a condition variable is typically provided by the operating system. or by the API, programming API, and it's associated, as the name says, with a condition that you define, and that condition is typically measured or dependent on a set of shared variables, and the shared variables, of course, they need to be protected by some logs. So you have variables that are shared between multiple threads, and you have a log associated, and you have the condition variable, and so the condition variable is used to synchronize and recheck the condition when there are any changes on those variables, and a thread waits on a certain condition to be true. And the other threads that don't wait on the condition but that manipulate the variables, they then signal the condition variable so that this one thread potentially waiting for a condition can then recheck the condition, and as soon as the condition is true, it can proceed in its with the data being logged. So the condition variable itself frees the log as long as the thread waits until the signal arrives. This is kind of complicated, but I hope that I explained the key ideas of it.
Okay. Back to the list of things we can do to avoid resource problems using the reactor pattern. I guess thread pools is a huge topic there too.
Yeah, thread pools and memory pools, pooling in general is important here, and the thread pools and memory pools, they allow to minimize the acquisition overhead and limit the resource consumption. And in the case of thread pools, a thread pool creates normally a set of threads in advance, uses those threads, so individual parts of the application can acquire a thread from the thread pool and release it back to the thread pool. The threads themselves, they wait typically on a condition variable until their service routine is set on which they should execute.
Okay, so we avoid the overhead of creation of threads on the fly, but we have, of course, the problem that we have this pool full of resources blocked all the time.
Right, and so there are then various strategies on how to destroy threads when they are no longer used, or how to acquire new threads, create new threads when the existing number of threads are not sufficient anymore, when there is a higher demand. And those properties on how much to eagerly acquire, how much to later then acquire on-demand threads, this is a configuration option, and really depends on how and when you optimize your system.
Okay. Of course, the pools are not only used for threads, especially in server or application server development. You have this for almost all resources, as you have many parallel threads. So pooling is very important on the server side.
Yeah. So another important thing learned from the design of concurrent and highly scalable servers was to minimize the usage of queues, to avoid memory allocations, and to avoid jitter. So queues are really good when you want to decouple between two threads in the pipes and filters design pattern. When you apply it in a concurrent setting, you have the queues as pipes between the filters, and the filters are executed typically in individual threads. So here it's inherent, but I would say as long as you can avoid it, as long as you don't really require a pipes and filter architecture, a concurrent one, then try to avoid queues, because firstly you don't minimize any availability or unavailability figures. saying when my system is busy, I have a queue, and the queue then just gets filled as long as it's not available. But any queue will be full at one point in time, so you just delay the failure, and you don't really avoid a availability failure.
But isn't this exactly the point from the beginning of our show? I mean, if you have, I wouldn't say many, but sufficient number of queues, you optimize for throughput, but not for latency. So you have to judge every time you use it if one or the other is better, and if you want more throughput of your server or more latency.
Yeah, but the throughput can be also reduced when you have dynamic memory allocations on your queues. So this, I would say, it's a trade-off between better decoupling your system and having individual threads for single tasks, and versus having better latency and smaller jitter and maybe somewhat higher throughput.
Mm-hmm. Okay, I understand.
And but now coming back to the reactor and using the reactor in multi-threaded environments, when you use the reactor in a multi-threaded environment, it's advisable to use a thread pool, as we just learned, to have the resources, the consumed resources under control. But then we have all kinds of problems. For example, how should multiple threads wait on a single and shared set of resources? Mm-hmm. And here the leader-followers pattern comes into play. The key of this pattern is that it nicely organizes and manages how the threads pick up work from the event sources, and how they can then later, for example, wait dedicated on dedicated responses that come through the event source. It works like that you always have a leader as long as a thread is waiting on the event source, and that the other threads take over the role of a follower, and the followers again wait on a condition variable until they are signaled to either pick up their response that they are waiting for, or to become the leader. And the leader is the only one who actually reads from the event source. And when the leader, for example, recognizes that this event is not designated for its event handler, for its execution, then it can signal the followers to deal with that special event.
Okay, so is this kind of a pipes and filters architecture, or am I getting it wrong?
No, it's pipes and filters is different. You have multiple threads that are generally not distinguishable from each other as long as they didn't execute any code yet.
Mm-hmm. Okay.
And so they are all equally important. They have all the same roles initially,
mm-hmm.
but when they wait on the event source, they take on temporarily the role of a leader or a follower.
Okay.
But then later they don't really exchange the data between them unless the leader gets a response that is designated to a follower. That is the only interaction among them.
Okay.
Only in this case. But else they pick up the work, do the work, and go back to the event source to listen on it and receive the next events.
Okay. We spoke a lot about the problems with Reactor and all this design stuff, but of course there are benefits too.
Yeah, I mean the benefit of using the Reactor in a multi-threaded environment is that here you can really make use of multiple CPUs, and you have typically a higher CPU utilization, so that you may even want to monitor your CPU utilization so that it doesn't grow you out of control, and that you can also run other monitoring applications or other applications on that server as well, and that it doesn't grab all your resources available when there's a high load from the users or from other systems that trigger events on your system.
Okay. Okay. I also heard about asynchronous IO that is used in server development to speed things up. Can you say a bit on this too?
Yeah, asynchronous IO is really an excellent thing. It's doing things asynchronously, not waiting on a read even when you know that a read is can be performed without waiting, but that you don't even have to wait till the read finishes. You can use the asynchronous I/O of some operating systems, for example, those that are POSIX conformant, and be notified on the completion of events. So instead of event arrival, as in the case of Reactor, with asynchronous I/O, you wait for the completion of events. And the pattern associated here is the proactor pattern, which tries to make the things a bit more easier, tries to give the developer a programming model on how to use the asynchronous I/O API of the operating system. Still, and nevertheless, I find asynchronous I/O programming very complicated, very tedious. I mean, it's proven that it's highly efficient, but it's so complex that it's well, I try to avoid it yet, and always try to use the reactive model and select operations instead of using the asynchronous I/O, because it also it's not available on every operating system, or the APIs are different, so you have a small porting issue here. In C++, for example, you can use ACE, the Adaptive Communication Environment by Doug Schmidt. This hides some of the complexity. Nevertheless, it's quite complicated.
Okay.
Another pattern associated in this domain is the asynchronous completion token, ACT, for associating responses with requests. So when you send the request asynchronously to another thread or to another peer process, whatever, and you get the response back and you want to associate it with the request that you sent. So when you have multiple responses outstanding, you can then associate this one specific response to the request that you initially sent.
Okay, so it's basically an ID or something like that.
Yeah, it's an ID, and you can use pointers with some limitations or just other unique means to identify a piece of data, essentially.
Okay, to sum it up, we now talked about how to build scalable servers, especially how to use the reactor pattern and all the problems that might be involved in there, the resource usage pooling, thread pooling. It seems still a complicated thing. Would you say the same?
Well, it's the patterns alleviated a bit, but nevertheless, multi-threaded server programming is something really difficult. And so I lately heard some interviews from other people, some podcasts. And the common opinion and the common trend when you look at application servers is that concurrency is best shielded from the application developer into the infrastructure. So you don't see many problems that way. But of course, the programming model and the concurrency model is then fixed, and you don't have so much space for optimizations.
Yeah.
For general purpose web servers and general purpose application servers, this is mostly okay, but when you want to squeeze out the last resources and the last bit of performance throughput, or when the general purpose application servers are not sufficient, you have to go and through the pain of building those systems, and maybe even with multiple threads.
Yeah. Maybe one last tip from me here. There are very good application servers out there that are open source. All that EJB stuff, the Tomcat and the Apache server. We have the great chance now to look into these servers, how they are built, and it's much easier than a few years ago to get knowledge on this stuff if you're really interested in how to build application servers.
Thanks for listening to another episode on Software Engineering Radio. We hope you liked it. In case you have a comment, leave us a comment at our site se-radio.net. Bye-bye.
Bye.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.